we're going to look at a concept called half-life. So let's start with first order. And just to give you an idea of half-life, the half-life of marijuana is 1.3 days. That means if you ingested marijuana somehow, in 1.3 days, 1/2 of the original amount would still be there. So what we're looking at is if you have a certain amount, let's say we have the concentration of A, and when half of it is left, that would be A divided by 2. So if we use that idea and our integrated rate law, so this would be our initial concentration, and half of that would be the half-life. So we take the initial concentration divided by 2. And then we still have it's equal to K times T 1/2. We're labeling this as 1/2 because it's the half-life now. So if we do all the math and cancel, this is what you end up for first order. So whenever a problem says it's a first order equation and it's asking you for the half-life, all you have to do is always use the 0.693 that comes from the math, divide by the rate constant, and you get the half-life. So let's look at a problem. If the half-life of a first order reaction is 20 minutes, what is the rate constant? So we use our formula and then rearrange, and we calculate our rate constant. So remember, this is only for first order. Okay, let's do the same for second order. So for second order, this would be our initial concentration divided by 2, and that would be our half of initial concentration. And then if you rearrange this equation, then you end up getting this. T 1/2 equals 1 over rate constant times the initial concentration of A. So if you have a second order, you always will want to use this for your half-life. Let's look at a problem. If the initial concentration is 0.6 molar, the rate constant is 7 times 10 to the 9 per molarity per second. For a second order reaction, what is the half-life? So keep in mind that because this is second order, we use this equation. Then we just plug in our variables and we solve for the half-life. Okay, let's discuss zero order kinetics. The rate law is rate equals K and the concentration of A to the 0. So we have 0, and that's why it's zero order. So if you simplify this, it's rate equals K to the 1, A to the 0 equals 1, or rate equals K. So if this is our rate law, and we do the calculus and integrate it, this would be our integrated rate law. It's in the form of the equation of y equals mx plus b. So if our initial concentration divided by 2 would be half, that would be our half-life. If we rearrange this and solve for T 1/2, we get T 1/2 equals A sub 0, initial concentration, divided by 2K. So you're going to want to use this when it's 0 order. So keep in mind that for each order, you will have a different equation to solve for the half-life. Let's do a practice problem. First of all, you want to be able to recognize this as an initial rates method question. You're given data for several experiments, and you're given the initial concentration of one of the products. So the question is asking us specifically with respect to B. That means you want to solve this one first. I chose rate 3 over rate 1. The reason I did that was because that would cancel. That ends up giving me 1 equals 2 to the power of y, and then y would be 0. So this means that the B is 0 order. So now the question is asking me with respect to A. So in this case, I chose rate 2 over rate 1. And that's because this would cancel. So when I do the math, I get 4 equals 2 to the x, and x must be 2. So this is second order with respect to A. Let's do another practice problem, since we're talking about 0 order equations. So this is giving us this reaction. It's 0 order. We're given the rate constant, room temperature. The initial concentration of A was 0.001 molarity. After 5 minutes, the rate is, and we have to solve for the rate. Well, if we remember that it's 0 order kinetics, and this is our rate law, the rate equals the rate constant. So this is your rate. It seems like there is a lot going on, but if you organize it, it's not as bad. So you're going to want to make a table for yourself to organize this. The rate law, rate equals K A to the 0. I like to do it this way because it reminds me this is 0 order, and then I can simplify this. First order, it's A to the 1. Second order, it's A to the 2. Remember, the way that we get the integrated rate law is by integrating this. So the calculus gives us this for the integrated rate law for 0 order. This is our integrated rate law for first order. This is our integrated rate law for second order. This is in the form of the equation of y equals mx plus b. So if we plot this as our y, and then this is our x, we would get a straight line if it was 0 order. So what we're saying here is, let's say you have data. You plot the data in 3 different graphs. One of your graphs is concentration of A versus time. One of your graphs is natural log of A versus time. And one of your graphs is 1 over A versus time. So given that data, whichever graph is most linear, that would tell you the rate. So this is a fair game question that some professors will ask you, and they might even ask you to do it on graph paper and do this by hand. So from the line, we get the slope for 0 order, the slope for 1st order, the slope for 2nd order. Then we calculated that the half-life for 0 order would be this equation. So T1/2 equals this. The half-life for first order is T1/2 equals this. The half-life for 2nd order is T1/2 equals this. So this is a very nice table to try to organize it for your brain. Okay, that's it for now.